Hello class. In this video we'll be reviewing the remaining geometry assumptions and principles that we've learned about so far this year. First we have the triangle congruence criteria, and let's start with side angle side. So they give us this parallelogram here, and we want to figure out, okay, well how can we satisfy side angle side with it, and what rigid motion could we use to map one of these triangles onto the other one? So how can we prove that they're congruent with side angle side? Give that a shot and I'll show you my answer. So first property I used is that you know that the opposite sides are equal in measure in a parallelogram. And then I said, hey, well these sides are parallel, so we know that we have congruent alternate interior angles. And then finally, that side in the middle is congruent to itself by the reflexive property. So then those two triangles are congruent. And what rigid motion will map one onto the other? Well, to do it in one step, you could just say that you rotate around the midpoint of side AC. Okay, next we have angle, side, angle, and side, side, side. So in this first picture, they tell us that we have a reflection. We want to know how can we use the fact that we have a reflection to satisfy angle, side, angle. Once again, give that a try, and then we'll look at it together. So first, we have angle AEB congruent to angle CED. And you could talk about this property of reflections or that we have vertical angles there in this case. And we also have BE equal to DE because we know that reflections preserve segment length. And we also have angle B congruent to angle D. My diagram's a little bit crowded here, sorry. And so now we have angle satisfied, right? The side has to be in the middle. It has to be the included side. And in this third picture, we want to show that we can that these triangles are congruent by using side, side, side. And they give us circles. And circles have the property that any point on the circle is the same distance from the center as any other point on it, right? They're all equidistant from that center. So we know that, well, AC, the segment that connects the centers, that's a common side. So we can use reflexive property there. And how do the circles help us? Well, we know that AB and AD are equal because they're radii of the same circle. And the same holds for BC and DC. Right, those are radii of the bigger circle. So now we have side, side, side satisfied. Angle, angle, side. So we learned in the lesson that angle, angle, side is really the same as angle, side, angle. So why is that true? Think about that for a moment. Well, here's the explanation. And basically it has to do with the fact that you know that the third pair of angles are congruent when you have two of them congruent. So for example, if we have angle EAB congruent to angle ECD, and we have angle ABE congruent to angle CDE, and let's say BE congruent to DE. So we have angle, angle, side satisfied. Well, in this diagram, you can either say that, oh, we have vertical angles there, right? So you could have also said that those are congruent, so that would satisfy side, angle, side. I'm sorry, angle, side, angle. Okay, that looks a little bit nicer. So if we have angle, angle, side, angle, side, angle is also true because those third angles are congruent. And even if they weren't vertical angles, you would still know that because you know that all three must add to 180. So the only way for that to work, if you have two pairs congruent, is that the third pairs have to be congruent. The third set of angles. And here we have a perpendicular bisector of an isosceles triangle. And we want to show that they're congruent by using a hypotenuse leg. A few ways to go about that. So that's what we want to prove. And we know that CD is perpendicular to AB because it gives us that. It's a perpendicular bisector. So these are both right angles. Okay, now we need legs and hypotenuse is congruent. Well, you know, CD is in both of them, so that's reflexive properties. That's a pair of legs. And we know that it's isosceles, so the legs have to be congruent. They really should have said that C is the vertex angle. That's what it intended here. So these two are congruent. So there we go. Then we would have hypotenuse leg satisfied. Let's look at some properties of parallelograms and triangles that we learned. We want to prove that we have a parallelogram here. We know that BE is congruent to DE, and angle CBE is congruent to angle ADE. We know that in the parallelogram, opposite sides are going to be congruent, the opposite angles are going to be congruent, and the diagonals bisect each other. So we should be thinking about those properties. And I think maybe one easy way to solve this is to use that first property, the opposite sides are congruent. So how can we prove that they're congruent? Well, we know that we have these vertical angles congruent to each other. Oops. So angle BEC and DEA are congruent to each other. So we have angle side angle satisfied. And let's see, that information was given to us, so altogether we have angle side angle. And since the triangles are congruent, well, we know about their corresponding pieces, they're also congruent or equal in measure. So we have one pair of sides congruent. And using a similar argument, we could show that BEA, triangle BEA, is congruent to triangle DEC. It would involve some angle addition and subtraction because you want us to show that angle ABD is congruent to angle CDB. But that's not a very long argument. So you'd end up with these two being congruent. And so since opposite sides are congruent, you have a parallelogram. We learned two important properties of the midsegment. We have a midsegment and a triangle. It is parallel to the third side, and it is also half the length of the third side. The side it doesn't touch. And let's see. So we have a midsegment here, and we want to figure out what the perimeter is. Since we do have a midsegment, we know that this has to be double 12, so BA is 24. And then to find the perimeter, you would add up everything on the outside. So you have a 16, another 16, a 24, a 20, and a 20. That gives us 96. And we learned in centroids that the centroid splits the median so that from the vertex to the from the vertex to the centroid is 2/3 of the total length, and from the centroid to the midpoint is 1/3 of the total length. So using that property, how can we figure out what the missing pieces are here? Well, you know AG is 12, so GE is going to be half that, 6. And let's see, to find BG, that's from the vertex to the centroid. And so since this is 5, it must be double, 10. And let's see, CD is the whole median. And we know that the small piece here, from the centroid to the midpoint, is 8. And so it's going to be triple that, 24. In this lesson, we went over the rest of the geometry assumptions and principles that we learned about this year. Thanks for watching this video.